In this final video of the week, we'll be reviewing some notation and ideas to support your reading and lab work. I'll be recapping some ideas from earlier videos and trying to draw things together. The idea of supervised learning is to build models of the relationship between predictor variables, which we'll call x, and a response variable y. Note that in general we'll have a number of different predictors, and we'll usually denote the number of predictors by p. On the right you can see a typical example. This is a dataset from the book Modern Applied Statistics with S. It shows the acceleration of a motorcycle during a crash as a function of time. You can see that the motorcycle starts off at roughly constant velocity, so zero acceleration, and then experiences rapid deceleration during the crash. The points seem to lie close to a smooth curve, as our physical intuition would expect. The curve shown in blue was actually estimated from the data using what's called a generalized linear model. This is a method we'll learn about later in the module. Note though that what we can see in the data is a noisy function of time. There's quite a bit of variability around the blue curve. In the models we develop, we'll explicitly acknowledge the existence of variability in the data beyond what's predicted by the model, and we'll do this by including an error term. We'll write our models in general as shown. The relationship we're trying to capture is given by f, and the error is modeled as the random variable epsilon. Where the response variable is numerical, we speak of a regression problem. The name comes from linear regression, which we'll say a lot more about in future work. But even when we're capturing a more complex relationship, which is non-linear, such as in the acceleration example we've spoken about, we'll still refer to a regression problem if we have a numerical response variable. There are many practical examples of such problems that occur throughout science, engineering, business, and beyond. And if you've encountered any statistical model before in your life, it was most probably a regression problem. Regression problems occur quite generally when we're trying to capture relationships between experimental or observed variables, and we might just call this first point modeling, understanding relationships between variables. They also occur when we're calibrating instruments or aligning two different types of measurement on the same process. And of course, they're widely used in business and beyond for making forecasts, which is to say predictions of what might happen in the future based on relationships that have held statistically in similar situations in the past. Classification problems form the main other type of situation that we'll be studying in this module. In general, what we mean by a classification problem is one in which the response variable is not numerical. In other words, it's a categorical variable. Classification problems occur whenever an automated system needs to make decisions based on noisy data. In medicine, for example, we might have a combination of test results and we need to decide whether or not the patient suffers from a condition. So we're trying to diagnose disease. Or perhaps in retail finance, we might have a system that has to decide quite rapidly, based on background information, whether or not a transaction is genuine or fraudulent. Now these examples are both binary classifications. Essentially it's an accept versus reject decision. But multi-category classification problems with more than two categories, as shown in the figure on the right, are also pretty common. When we solve a classification problem, what we're trying to do is draw boundaries that easily, neatly separate the classes. That's fine if they're well separated, but if the classes are not well separated, what we're always trying to do is to choose a threshold that minimizes the amount of misclassification. So classification problems, what we're trying to do is build a model for good boundaries between classes. Many of the models that we encountered in supervised learning are parametric models. That is to say, they assume a particular functional form for f. The linear model is a common example. There are of course more general families, however, which we'll meet throughout the module. The key thing that they have in common is the existence of a relatively small number of 3 parameters which we estimate using the data. By placing restrictions on f, we make the problem of finding good models much more tractable. All that we need to do for a parametric model is to determine good values for the parameters, and generally it's much easier to do this than to estimate whole functions more generally. For a parametric model, we use a loss function to determine how badly a particular member of our function class does its job. Now that job is usually predicting y using x, so our loss function is going to depend on y as well as depending on our prediction, which I'm going to call f hat of x. Perhaps the most common choice for our loss function is the squared error loss, so that gives us y minus f hat of x, so we take the difference between the true value y and our prediction, and we square that value. Ultimately, this comes from Euclidean distance. You can see a typical regression line on the right, and we can use this to motivate the idea of squared error loss. When we fit a regression line, we typically sum the squares of the errors. Here's an error, the error for the ith observation, and we choose our line by minimizing the sum of the squares of the errors. So from I is 1, in this case, up to 5. Why do we use this loss function? Well, it's because we're thinking of these 5 data points as a single point in 5D Euclidean space. And this represents the distance function in that space. So as soon as we start to think in terms of vectors and matrices, the squared error loss function becomes very natural. If we take x as some fixed value little x, so we condition on the value x, we're going to choose our estimator f hat as a function of little x. We choose f hat of x as the minimizer. Is going to minimize our loss function averaged over the distribution of y. So it's going to be minimizing the expectation of y minus f of x, which is our loss function, squared, that's our loss function, conditional on x equals little x. So that's going to be the form that our model, our minimizer, takes. We're going to show in the lab the following fact, which is true in general for this loss function, and that fact is that f hat of x, which is the minimizer of this function, is nothing more than the conditional expectation of y given that x is little x. We can define other loss functions. For example, the L1 loss between y and f hat of x is nothing more than just the absolute value of the difference between y and f hat of x. So then we minimize, for this loss function, we minimize the expectation over y of y minus f hat of x, again conditional on x equals little x. This gives us our minimizer as a function of little x. This loss function is less sensitive to outliers, less sensitive to unusual observations, which is very useful in many applications. And for this loss function, we end up with another nice property that f hat of x is the conditional median. Of y, conditional on x equals little x. There's also a nice property. So for L1 we have the conditional median, and for L2 we have the conditional mean. In supervised learning, our representation of y as f of x plus epsilon could be thought of as decomposing the data into signal and noise. And because we're decomposing the data into two terms, there are two different ways of getting things wrong. The first of these, which you can see on the left, is underfitting. And in underfitting, the model is mistaking signal for noise. Some of the signal, therefore, remains unmodeled. What's going on here is that the parametric family that we've used is not rich enough. The model is making too many assumptions, so even the best possible memory of our parametric family misses important features of the data. And we can see that here. Important features of the data are completely ignored by a model that only wants to fit a straight line. Our family of possible models is simply not rich enough. And then on the right, we have what we might call the opposite mode of failure, and that's overfitting. And here, the model mistakes noise for signal. Which is why I call it the opposite way of getting things wrong. And the very flexible models that one encounters in machine learning are very prone to this second mode of failure. Here what's going on is that our parametric family is too rich. It's so flexible that it accommodates fluctuations in the data that are due to the errors epsilon and not due to f. So what goes wrong here is that the model will fail badly on unseen observations. Overfitting tends to occur when the model has high variance. What this means is that slightly different training data would lead to a very different model fit. In this case, what's going on is there are nearly as many free parameters as there are data points. And this means that effectively, each parameter is estimated using only a small sample size. And this means that our estimates, and therefore our model, is unreliable. You'll explore this idea in much more depth in this week's lab and in the reading. And this is just the very beginning of some ideas that we're going to be developing all through the term.